Section 10. Hysteresis and effective resistance. If an alternating current OI prime equals I in figure 15 passes through a circuit of reactance X equals 2 pi NL and of negligible resistance, the magnetic flux produced by the current O phi equals phi is in phase with the current, and the electromotive force induced by this flux, or counter-electromotive force of self-induction, OE double prime equals E double prime equals XI, lags 90 degrees behind the current. The electromotive force consumed by self-induction, or impressed electromotive force, OE prime equals E prime equals XI, is thus 90 degrees ahead of the current. Inversely, if the electromotive force OE prime equals E prime is impressed upon a circuit of reactance X equals 2 pi NL and of negligible resistance, the current OI equals I equals E prime over X lags 90 degrees behind the impressed electromotive force. This current is called the exciting or magnetizing current of the magnetic circuit and is wattless. If the magnetic circuit contains iron or other magnetic material, energy is consumed in the magnetic circuit by a frictional resistance of the material against a change of magnetism, which is called molecular magnetic friction. If the alternating current is the only available source of energy in the magnetic circuit, the expenditure of energy by molecular magnetic friction appears as a lag of the magnetism behind the magnetomotive force of the current, that is, as magnetic hysteresis, and can be measured thereby. Magnetic hysteresis is, however, a distinctly different phenomenon from molecular magnetic friction, and can be more or less eliminated, as for instance by mechanical vibration, or can be increased without changing the molecular magnetic friction. In consequence of magnetic hysteresis, if an alternating electromotive force OE prime equals E prime is impressed upon a circuit of negligible resistance, the exciting current, or current producing the magnetism, in this circuit is not a wattless current, or current of 90 degrees lag, as in figure 15, but lags less than 90 degrees by an angle 90 minus alpha, as shown by OI equals I in figure 16. Since the magnetism O phi equals phi is in quadrature with the electromotive force E prime due to it, angle alpha is the phase difference between the magnetism and the magnetomotive force, or the lead of the magnetomotive force, before the magnetism. It is called the angle of hysteretic lead. In this case, the exciting current OI equals I can be resolved into two components. The magnetizing current OI sub 2 equals I sub 2, in phase with the magnetism O phi equals phi, that is, in quadrature with the electromotive force, OE double prime equals E double prime, and thus wattless. And the magnetic energy current, or hysteresis current, OI sub 1 equals I sub 1, in phase with the electromotive force OE double prime equals E double prime, or in quadrature with the magnetism O phi equals phi. Magnetizing current and magnetic energy current are the two components of the exciting current. If the alternating circuit contains, besides the reactance X equals 2 pi NL, a resistance R, the electromotive force OE prime equals E prime in the preceding figure 15 and figure 16 is not the impressed electromotive force, but the electromotive force consumed by self-induction or reactance and has to be combined, figure 17 and figure 18, with the electromotive force consumed by the resistance, OE double prime equals E double prime equals IR, to get the impressed electromotive force OE equals E. Due to the hysteretic lead alpha, the lag of the current is less in figure 16 and figure 18, a circuit expending energy in molecular magnetic friction, than in figure 15 and figure 17, a hysteresis-less circuit. As seen in figure 18, in a circuit whose ohmic resistance is not negligible, the magnetic energy current and the magnetizing current are not in phase and in quadrature, respectively, with the impressed electromotive force, but with the counter-electromotive force of self-induction, or electromotive force consumed by self-induction. Thus, the magnetizing current is not quite wattless, as obvious, since energy is consumed by this current in the ohmic resistance of the circuit. Resolving in figure 19, the impressed electromotive force OE equals E in two components, OE sub 1 equals E sub 1 in phase, and OE sub 2 equals E sub 2 in quadrature with the current OI equals I. The energy electromotive force OE sub 1 equals E sub 1 is greater than E double prime equals IR, and the wattless electromotive force OE sub 2 equals E sub 2 less than E double prime equals IX. The value R prime equals E sub 1 over I, energy electromotive force over total current, is called the effective resistance. And the value X prime equals E sub 2 over I, wattless electromotive force over total current, is called the apparent or effective reactance of the circuit. Due to the loss of energy by hysteresis, eddy currents, etc., the effective resistance differs from and is greater than the ohmic resistance, and the apparent reactance is less than the true or self-inductive reactance. The loss of energy by molecular magnetic friction per cubic centimeter and cycle of magnetism is approximately W equals eta times B to the power 1.6, where B is the magnetic induction in lines of magnetic force per cubic centimeter, W is energy in absolute units, or ergs per cycle, equal to 10 to the power minus 7 watt-seconds, or joules, and eta is called the coefficient of hysteresis. In soft annealed sheet iron or sheet steel, eta varies from 1.25 times 10 to the power minus 3 to 4 times 10 to the power minus 3, and can, in average for good material, be assumed as 2.5 times 10 to the power minus 3. The loss of power in volume V at magnetic density B and frequency N is thus P equals Vn eta B to the 1.6 times 10 to the power minus 7 watts. And if I equals exciting current, the hysteretic effective resistance is R double prime equals P over I squared equals Vn eta 10 to the power minus 7 B to the 1.6 over I squared. If the magnetic induction B is proportional to the current I, it is R double prime equals An over I to the power A. That is, the effective hysteretic resistance is inversely proportional to the square of the current and directly proportional to the frequency. Besides hysteresis, eddy or Foucault currents contribute to the effective resistance. Since at constant frequency the Foucault currents are proportional to the magnetism inducing them and thus approximately proportional to the current, the loss of power by Foucault currents is proportional to the square of the current, the same as the ohmic loss, that is, the effective resistance due to Foucault currents is approximately constant at constant frequency, while that of hysteresis decreases slowly with the current. Since the Foucault currents are proportional to the frequency, their effective resistance varies with the square of the frequency, while that of hysteresis varies only proportionally to the frequency. The total effective resistance of an alternating current circuit increases with the frequency, but is approximately constant within a limited range at constant frequency, decreasing somewhat with the increase of magnetism. Examples. A reactive coil shall give 100 volts electromotive force of self-induction at 10 amperes and 60 cycles. The electric circuit consists of 200 turns, number 8B and SG, S equals 0.013 square inch of 16-inch mean length of turn. The magnetic circuit has a section of 6 square inches and a mean length of 18 inches of iron of hysteresis coefficient eta equals 2.5 times 10 to the minus 3. An air gap is interposed in the magnetic circuit of a section of 10 square inches, allowing for spread to get the desired reactance. How long must the air gap be, and what is the resistance, the reactance, the effective resistance, the effective impedance, and the power factor of the reactive coil? 200 turns of 16-inch length and 0.013 square inch in section at resistivity of copper of 1.8 times 10 to the minus 6 have the resistance R1 equals 1.8 times 10 to the minus 6 times 200 times 16 divided by 0.013 times 2.54 equals 0.175 ohms, where the factor 2.54 reduces from inches to centimeters. E equals 100 volts induced, N equals 60 cycles, and N equals 200 turns. The maximum magnetic flux is given by E equals 4.44 N phi, or 100 equals 4.44 times 60 times 200 times phi, whence phi equals 0.188 million. This gives, in an air gap of 10 square inches, a maximum density B equals 18,800 lines per square inch, or 2,920 lines per square centimeter. 10 amperes in 200 turns give 2,000 ampere turns effective, or F equals 2,830 air turns maximum. Neglecting the ampere turns required by the iron part of the magnetic circuit, 2,830 ampere turns have to be consumed by the air gap of density, B equals 2,920. Since B equals 4F over 10L prime, The length of the air gap has to be L equals 4F over 10B. B equals 4 times 2,830 over 10 times 2,920 equals 1.22 centimeters, or 0.48 inches. At 6 square inches section and 18-inch mean length, the volume of iron is 180 cubic inches, or 1,770 cubic centimeters. The density in the iron BS equals 188,000 over 6 equals about 31,830 lines per square inch, or 4,850 lines per square centimeter. At hysteresis coefficient eta equals 2.5 times 10 to the minus 3, and density BS equals 4,850, the loss of energy per cycle in cubic centimeter is W equals eta B to the 1.6 equals 2.5 times 10 to the minus 3 times 4,850 to the 1.6 equals 2,220 ergs, and the hysteresis loss at N equals 60 cycles, and the volume V equals 1,770, is thus P equals 60 times V times 2,220 ergs per second equals 23.5 watts, which at 10 amperes represent an effective hysteretic resistance. R2 equals 23.5 over 10 squared equals 0.235 ohms. Hence, the total effective resistance of the reactive coil is R equals R1 plus R2 equals 0.175 plus 0.235 equals 0.41 ohms. The reactance is X equals E over I equals 10 ohms. Thus, the impedance Z equals 10.01 ohms, and the power factor P equals R over Z equals 4.1%. The total volt amperes of the reactive coil are I squared Z equals 1,001. The loss of power, I squared R equals 41. 10, 9, 8, 7, 6. Section 11. Capacity in condensers. The charge of an electric condenser is proportional to the impressed voltage and to its capacity. A condenser is called of unit capacity if unit current flowing into it during 1 second produces 1 unit difference of potential at its terminals. The practical unit of capacity equals 10 to the minus 9 absolute units. It's called a farad. 1 farad is an extremely large capacity, and 1/millionth of 1 farad is commonly used, and called 1 microfarad MF. If an alternating electromotive force is impressed upon a condenser, the charge of the condenser varies proportionally to the electromotive force, and thus current flows into the condenser during rising, out of the condenser during decreasing electromotive force, as shown in Figure 20. That is, the current consumed by the condenser leads the impressed electromotive force by 90 degrees, or a quarter of a period. If N equals frequency, E equals effective alternating electromotive force impressed upon a condenser of C microfarad capacity, the condenser is charged and discharged twice during each cycle, and the time of one complete charge or discharge is thus 1 over 4N. Since E times square root 2 is the maximum voltage impressed upon the condenser, an average of CE times square root 2 times 10 to the minus 6 amperes would have to flow during 1 second to charge the condenser to this voltage, and to charge it during 1 over 4N seconds. Thus, an average current of 4N CE times square root 2 times 10 to the minus 6 amperes is required. Since effective current over average current equals pi over 2 square root 2, the effective current I equals 2 pi N CE times 10 to the minus 6, that is, at an impressed electromotive force of E effective volts and frequency N, a condenser of C microfarads consumes a current of I equals 2 pi N CE times 10 to the minus 6 amperes effective, which current leads the terminal voltage by 90 degrees, or a quarter period, or inversely, E equals 10 to the 6th I over 2 pi N C equals X dI. The value XD equals 10 to the 6th over 2 pi N C is called the capacity reactance of the condenser. Due to the energy loss in the condenser by dielectric hysteresis, the current leads the electromotive force by somewhat less than 90 degrees and can be resolved into a wattless charging current and a dielectric hysteresis current, which latter, however, is so small as to be generally negligible. The capacity of one wire of a transmission line is C equals 1.11 times 10 to the minus 6 times L over 2 log base E of 2D over D minus square root 2 microfarads, where D equals diameter of wire, centimeters, D equals distance of wire from return wire, centimeters, L equals length of wire, centimeters, 1.11 times 10 to the minus 6 equals reduction coefficient from electrostatic units to microfarads. The logarithm is the natural logarithm, thus in common logarithm, since log base e of a equals 2.803 log base 10 of a, the capacity is C equals 0.25 times 10 to the minus 6 times L over log base 10 of 2 d over d, because of the reduction microfarads. The derivation of this equation must be omitted here. The charging current of a line wire is thus I equals 2 pi n C E times 10 to the minus 6, where n equals the frequency, E equals the difference of potential effective between the line and the neutral, E equals 1/2 line voltage in a single phase or 4-wire quarter phase system, 1 over square root 3 line voltage or Y voltage in a 3-phase system. In the transmission line discussed in the examples in sections 7, 8, and 9, what is the charging current of the line at 6,000 volts between lines and 38.3 cycles? How many volt amperes does it represent, and what percentage of the full load current of 44 amperes is it? The length of the line is, per wire, L equals 2.2 times 10 to the 6 centimeters. The distance between wires, D, equals 45 centimeters. The diameter of transmission wire, D, equals 0.82 centimeter. Thus, the capacity per wire, C, equals 0.25 times 10 to the minus 6 times L over log base 10 of 2D over D equals 0.27 microfarad. The frequency is N equals 33.3. The voltage between lines, 6,000. Thus, per line, or between line and neutral point, E equals 6,000 over square root 3 equals 3,460. Hence, the charging current per line, I0 equals 2 pi NCE times 10 to the minus 6 equals 0.195 amperes, or 0.443% of full load current, that is negligible in its influence on the transmission voltage. The volt ampere input of the transmission is 3I0E equals 2000 equals 2.0 kilovolt amperes. Section 12, impedance of transmission lines. Let R equal resistance, X equals 2 pi NL equal reactance of a transmission line, E naught equals alternating electromotive force impressed upon the line, I equals current flowing over the line, E equals electromotive force at receiving end of the line, and omega equals angle of lag of current I behind electromotive force E. Omega less than 0 thus denotes leading, omega greater than 0 lagging current, and omega equals 0 a non-inductive receiver circuit. The capacity of the transmission line shall be considered as negligible. Assuming the current OI with bar equals I as 0 in the polar diagram. Figure 21, the electromotive force E is represented by vector OE ahead of OI by angle omega. The electromotive force consumed by resistance R is OE sub 1 equals E sub 1 equals IR in phase with the current. And the electromotive force consumed by reactance X is OE sub 2 equals E sub 2 equals IX 90 degrees ahead of the current. Thus, the total electromotive force consumed by the line, or electromotive force consumed by impedance, is the resultant OE sub 3 of OE sub 1 and OE sub 2, and OE sub 3 and his E sub 3 equals IZ. Combining OE sub 3 and OE gives OE naught, the electromotive force impressed upon the line. Denoting tangent alpha equals X over R, the lag angle of the line impedance. It is trigonometrically, by the law of cosines on the triangle formed by OE, EE sub 3, and OE naught, that E naught squared equals E squared plus E sub 3 squared plus 2 times E sub 3 times the cosine of open parentheses alpha minus omega close parentheses. Interpreting this identity in the more convenient half-angle form, the same relation can be written as E naught equals the square root of open parentheses E plus IZ close parentheses squared minus 4, EIZ times sine squared of 1/2 of open parentheses alpha minus omega close parentheses. This is the key sending end voltage formula for a short line with resistance and reactance, and the drop of voltage in the line, the difference between impressed and received voltage, is therefore E naught minus E equals the square root of open parentheses E plus IZ close parentheses squared minus 4, EIZ times sine squared of 1/2 of open parentheses alpha minus omega close parentheses minus E. That is, the voltage E naught required at the sending end of a line of resistance R and reactance X delivering current I at voltage E, and the voltage drop in the line do not depend upon current and line constants only, but depend also upon the angle of phase displacement of the current delivered over the line. If omega equals 0, that is non-inductive circuit, E naught equals the square root of open parentheses E plus IZ close parentheses squared minus 4 EIZ sine squared of alpha over 2, that is less than E plus IZ, and thus the line drop less than IZ. If omega equals alpha, E naught is a maximum equals E plus IZ, and the line drop is the impedance voltage. With decreasing omega, E naught decreases and becomes equal to E. That is, no drop of voltage takes place in the line at a certain negative value of omega, which depends not only on Z and alpha, but on E and I. Beyond this value of omega, E becomes smaller than E. That is, a rise of voltage takes place in the line due to its reactance. This can be seen best graphically. For the same electromotive force E received, but different phase angles omega, all vectors OE lie on a circle E with O as center. Figure 22. Vector OE sub 3 is constant for a given line and given current I. Since E naught times OE naught equals constant, E naught lies on a circle E naught with E sub 3 as center and OE equals E as radius. To construct the diagram for angle omega, OE is drawn under angle omega with OI and EE naught parallel to OE sub 3. The distance EE naught between the two circles on vector OE naught is the drop of voltage, or rise of voltage, in the line. As seen in figure 23, E naught is maximum in the direction OE sub 3, that is, for omega equals alpha, and is less for greater as well as for smaller angles omega. It is equal to E in the direction OE naught double prime, in which case omega is less than 0, and minimum in the direction OE naught triple prime. The values of E corresponding to the generator voltages E naught prime, E naught double prime, E naught triple prime, E naught quadruple prime are shown by the points E prime, E double prime, E triple prime, E quadruple prime, respectively. The voltages E triple prime and E quadruple prime correspond to a wattless receiver circuit, E double prime prime and E triple prime prime. For non-inductive receiver circuit O, E triple prime double prime, the generator voltage is OE naught triple prime double prime. That is, in an inductive transmission line, the drop of voltage is maximum and equal to IZ if the phase angle omega of the receiving circuit equals the phase angle alpha of the line. The drop of voltage in the line decreases with increasing difference between the phase angles of line and receiving circuit. It becomes 0 if the phase angle of the receiving circuit reaches a certain negative value, leading current. In this case, no drop of voltage takes place in the line. If the current in the receiving circuit leads more than this value, a rise of voltage takes place in the line. Thus, by varying phase angle omega of the receiving circuit, the drop of voltage in a transmission line with current I can be made anything between IZ and a certain negative value. Or inversely, the same drop of voltage can be produced for different values of the current I by varying the phase angle. Thus, if means are provided to vary the phase angle of the receiving circuit by producing lagging and leading currents at will, as can be done by synchronous motors or converters, the voltage at the receiving circuit can be maintained constant within a certain range, irrespective of the load and generator voltage. In figure 24, let OE equal E, the receiving voltage, I, the energy current flowing over the line. Thus, OE sub S equals E sub S equals IZ, the electromotive force consumed by the impedance of the energy current consisting of the electromotive force consumed by resistance OE sub 1, and the electromotive force consumed by reactance OE sub S. Wattles currents are represented in the diagram in the direction OA when lagging and OB when leading. The electromotive force consumed by impedance of these Wattles currents is thus in the direction E prime at right angles to OE subs. Combining OE subs and OE gives the electromotive force OE sub S prime, which would be required for non-inductive load. If E naught is the generator voltage, E naught lies on a circle E naught with OE subs as radius. Thus, drawing E sub S E naught parallel to E prime gives OE naught the generator voltage, OE sub S prime equals E sub S E naught, the electromotive force consumed by impedance of the Wattles current, and proportional thereto, OI prime equals I prime, the Wattles current required to give at generator voltage E naught and energy current I the receiver voltage E. This Wattles current I prime lags behind E sub S prime by less than 90 and more than 0 degrees. In calculating numerical values, we can either proceed trigonometrically as in the preceding, or algebraically by resolving all sine waves into two rectangular components. for instance, a horizontal and vertical component, in the same way as in mechanics when combining forces. Let the horizontal components be counted positive towards the right, negative towards the left, and the vertical component positive upwards, negative downwards. Assuming the receiving voltage as zero line or positive horizontal line, the energy current I is the horizontal, the Wattles current I prime the vertical component of current. The electromotive force consumed by resistance is the horizontal component with the energy current I, and the vertical component with the Wattles current I prime, and inversely the electromotive force consumed by reactance. We have thus, as seen from figure 24, the following rectangular components: receiver voltage E, horizontal plus E, vertical 0; energy current I, horizontal plus I, vertical 0; Wattles current I prime, horizontal 0, vertical plus or minus I prime; electromotive force consumed by resistance R of energy current I, R, horizontal plus IR, vertical 0; electromotive force consumed by resistance R of Wattles current I prime R, horizontal 0, vertical plus or minus I prime R; electromotive force consumed by reactance X of energy current IX, horizontal 0, vertical minus IX; electromotive force consumed by reactance X of Wattles current I prime X, horizontal plus or minus I prime X, vertical 0. Thus, total electromotive force required, or impressed electromotive force E naught, has the rectangular components, horizontal E plus IR plus or minus I prime X, and vertical plus or minus I prime R minus IX. Hence combined, the magnitude of the generator voltage is E naught equals the square root of open parenthesis E plus IR plus or minus I prime X, close parenthesis squared, plus open parenthesis plus or minus I prime R minus IX, close parenthesis squared. Or using the cancellation of cross terms, the same result can be written compactly as E naught equals the square root of E squared plus 2E times open parenthesis IR plus or minus I prime X close parenthesis plus Z squared times open parenthesis I squared plus I prime squared close parenthesis. From this equation, I prime can be calculated, that is, the Wattles current found, which is required to give E naught and E at energy current I. The lag of the total current in the receiver circuit behind the receiver voltage is tangent omega equals I prime over I. The lead of the generator voltage ahead of the receiver voltage is tangent theta equals vertical component of E naught over horizontal component of E naught, which is plus or minus I prime R minus IX over E plus IR plus or minus I prime X. And the lag of the total current behind the generator voltage is omega naught equals omega plus theta. As seen by resolving into rectangular components, the phase angles are directly determined from these components. The resistance voltage is the same component as the current to which it refers. The reactance voltage is a component 90 degrees ahead of the current. The same investigation as made here on long-distance transmission applies also to distribution lines, reactive coils, transformers, or any other apparatus containing resistance and reactance inserted in series into an alternating current circuit.